Hello and welcome to our presentation on cyber-physical systems and spectrum sensing as a service. This is presented for Kennesaw State University IT Capstone for the fall semester of 2020. Our project owner is Sumit Chakravarti. Our instructor is Dr. Ying Ji. Our team members include Adam Block, Ryan LeBlanc, Scott Lilly, myself, Austin Mascarenas, and Wes McDonald. So we'll begin with a brief introduction and cite our objectives, go over cyber-physical systems, what they are and how they pertain to our project, review the environment that we worked in order to complete our project, go over spectrum sensing as a service, and federated learning and how it pertains to our project, review possibilities for future research, what lessons that we learned while working through the project, the challenges that we faced along the way and how we overcame them, and finally go through our conclusion and what it is we gained from the project. So the intent of this project was to investigate the use of reinforcement learning techniques to develop an artificial agent that will act as a control solution to augment spectrum sensing technology in cyber-physical systems. In addition, we took a look at federated learning, then compared them with our techniques to determine which system is more suited to the task. We conducted several different simulations. We will review the environment in which we conducted those simulations a little bit later in the paper in order to instruct an artificial agent in techniques to rapidly establish a connection on a dynamic ad hoc network and maintain that connection while avoiding data collision. Next, we need to do a review of cyber-physical systems, what they are, and how they interacted with our project. A cyber-physical system is any device where a physical mechanism is controlled by a computer-based algorithm and consists of three layers: the application control layer, the data transmission layer, and the perception execution layer. We go into more details on each of these layers in our paper. For the purposes of this project, we focused primarily on cyber-physical systems such as autonomous vehicles and how they connect to a network while in operation. Our aim is to improve the communication in this area that would benefit autonomous vehicles in having a fast and reliable connection to base stations so that base stations could better issue commands from the cloud. We look into techniques designed to rapidly connect to other devices, avoid collision or interference in transmissions, and maintain secure connections for as long as possible.
For our testing environment, our team used a virtual machine setup through VMware installed with Linux Ubuntu version 20.04, NS3, and NS3 Gem. Initially, our team pursued the use of Kennesaw's high-powered computing server for our testing purposes, but unfortunately, we were not able to acquire admin privileges, which was necessary to run any NS3 simulation. So after discussing this with our sponsor, we decided to switch our focus to NS3. NS3 is an open source discrete event network simulator and has various free toolkits that we could make use of for our project, mainly being NS3 Gem. NS3 Gem is an open source framework that integrates OpenAI Gem into NS3 for usage of reinforcement learning and network research. OpenAI Gem is a toolkit for reinforcement learning that is widely used in artificial intelligence research.
Spectrum sensing is a technique that looks at different frequencies and channels and tries to identify the best channel at given time, given scenario, and puts whatever is trying to reach that channel in there. Um, the goal of this project was to recognize a deep learning agent that uses it and then determine the pattern in it and uh, research and better understand what it was doing. So in this example, you're seeing spectrum sensing using reinforcement learning, and basically you're seeing what I talked about in the prior slide, where spectrum sensing is looking at every channel and it's determining the best channel to be in at said given time and when to leave. And within the graph below, you'll see at 0 to 50, it's figuring out what it's doing. So it's bouncing up and down, it's going to different intervals, it's staying different lengths of periods of time. And then after doing that, you see at roughly episode 100 that it's realizing that the best bang for its buck to be as efficient as possible and to prevent any possible of colliding or connection error is to sit in any given channel for about 15 seconds at a time. From there, after episode 100, you see it occasionally jump up to about 20 seconds, maybe 19, give or take. And basically, what it's doing is it's processing. It's just verifying that what it learned within the first 50 episodes to about 75 episodes, it's ensuring that that's what it was. It's reinforcing itself. And as you get further and further along the episode, you start seeing that there's less jumps and there's long gaps of just um, normalization, and that's what you're starting to capture at around episode 235, 240, and onward. So in this example, we wanted to see what would happen if we change the pattern of how it goes in each channel. So the way the code is set up is there's an array from 0 to 3. So there's 4 channels, and it starts off at 0, and it goes to 1, then 2, then 3, and then it starts back over at 0. So what we did, we wanted to see if there's any possible change, any different patterns, any kind of discrepancy that wouldn't match in the slide prior to this. So what we did is we changed the pattern to be 432, or sorry, 3210, and then start back over at 321. And as you can see, nothing really changed. 0 to 50, same thing. It was learning. 50 to 100, did its occasional jump, started realizing that best bang for the buck was about 15. And then it started to normalize roughly after 200. You start seeing less jumps and more normalization, and then kind of taper off at 300, where there's pretty much long periods of time where there was no jumping, and it figured that was the sweet spot. In our last example, we wanted to see how spectrum sensing handled channel closure. So, for example, maybe a node went down for a brief minute or two, or maybe in 5 minutes. Who knows? Maybe there's a cyber attack that's going on and they overtook a node or something. We wanted to see how the reinforcement learning worked within this simulated network. And within the graph, what you see is it's realizing that at the beginning there's less channels, and it's bouncing around like you see in all the other examples we've shown. It's bouncing back and forth, up low, up low, up low at the time, or sorry, low high, low high, low high at the time. And after about roughly, again, 55 to 75, it's realized that the longer I stay in this channel, the better off I am with success. And so you see that as soon as it gets to 75, 80, it realizes that's the best time. That's the best bang for my buck, because I don't have more allotted channels to move around in. So if I stay in these channels longer, I'll be able to successfully broadcast and stay connected longer. And that's what the graph is reflecting here. And then you can see where we've commented out in the code the channels. So lastly, one of the, I guess, drawbacks to this project is we didn't have the Q car, so we couldn't really build a network around it and really test in a, a simulated real world scenario with a car. But the data that we did get provided us with valuable information of what spectrum sensing is able to do with a reinforcement learning, deep AI learning tool with it. It potentially could be a viable option going forward when you start talking about CPS and building smart cities and developing those networks for autonomous vehicles to communicate to. It seems promising. Research is obviously continue needed as far as the cyber attacks goes, because you never know. without a cue card, we couldn't really simulate what happens when you hijack a node, or maybe you inject different packets and try to mimic the nodes and whatnot. So there is a lot of research that could be continued from this, and a lot of learning experience and opportunities from this.
Hello everyone, my name is Wes McDonald, and I'm here to talk to you about Spectrum Sensing as a Service, aka SPAS. We're going to begin by asking a question. Why scan for others in the first place? Well, there are three core incentives for spectrum sensing for others. The first is cooperative spectrum sensing. This is the most altruistic by saying sensors will sense for whoever they encounter for the greater good of all. The second is reciprocity-based sensing, which is the idea being as that a sensor will sense anything that also senses for it in turn. The third is social aware sensing, which means that a sensor will sense for friends and parties that it is interested in. Unfortunately, these motivations present low feasibility as business models. They don't make a lot of money and provide little incentive for a battery stripped sensing device to participate in. Let's talk about spectrum sensing as a service model. As a service, spectrum sensing is referred to as SPAS, or spectrum sensing as a service via smart contracts. In SPAS, a mobile network operator, or MNO, can purchase sensing services from nearby helper sensors. The MNO then defines its requirements and issues payment via cryptocurrency to the helper sensor in an Ethereum-based smart contract. The formula depicted below, as proposed by Bayhan and Associates, details how financial compensation can be calculated after being divided out by the presumed costs the helper sensor has saved the MNO. In short, the business feasibility of companies utilizing SPAS depends on the cost-benefit analysis of offloading spectrum sensing and issuing Ethereum smart contracts. So, in English, what that means is that the business feasibility of spectrum sensing as a service can be calculated with the potential savings SPAS provides minus the expenses SPAS takes to set up. So what are the explicit benefits of SPAS? Well, for one, built into the SPAS model, there are many possible avenues for saving money on operational costs for mobile network operators. A typical LTE base station, for example, performing spectrum sensing in-house, requires approximately 25 to 33% of that station's power budget in watts. Outsourcing spectrum sensing to a helper sensor can save this energy so that it can be used elsewhere, naturally. The same can also be said for the station's bandwidth use. So, by removing the need for requiring an MNO's assistance and being assigned to an open channel, SPAS could also cut back the number of processing cycles needed to search for an open channel and dedicate more processing towards important tasks such as improving autonomous vehicle operations, which was our key example. In conclusion, by utilizing SPAS, we can influence client nodes to perform spectrum sensing as a means to improve a base station's functionality, while additionally providing financial compensation to clients so that everyone benefits. Overall, SPAS can save energy, bandwidth, and processing cycles, preserving the operators of the base station money, as well as improve the general performance of all devices connected to it.
What is a federated system and how does it work? The Federated Learning System was developed by Google to create a decentralized way for smart devices to collaboratively learn a shared prediction model without needing to distribute the training data from the node to the cloud. The process begins when a node on the network downloads the current working model from the base station. Each node contributing to the problem will collect and learn from its own dataset and then push an updated prediction model to the base station, where it will then collectively aggregate the new models from each node in the cloud, average it, and then distribute a new model to be evaluated. As a result, the federated learning system helps nodes by training them with enhanced models while they operate under a system which has lower latency, consumes less power, and keeps the training data idiosyncratic. In practice, nodes connecting to the network would receive a model from the base station that indicates which channels are currently occupied, and by using a spectrum sensing agent, they can determine which channels are most primed to connect to. Nodes would each have a predetermined channel preference that would be shared alongside the prediction model sent to the base station, and the base station would then distribute an updated model as well as confirm or deny a node's request to join a particular channel. This system helps to guarantee that a node on the network would be placed onto its favored channel, while also aiding to guide other nodes which have not been connected yet. In theory, a federated learning system should yield the strongest channel and reduce the amount of potential data collisions when compared to SPAS, since each node is receiving a channel mapping model that will help them determine the most noise-free channel. The downside to using the federated learning method is that it will require more processing cycles and energy consumption, considering that it will need to regularly forward learning models to the cloud, as well as distribute new models to the nodes. While federated learning systems can help reduce energy consumption from base stations, similarly to the problems we face with the traditional system, it remains difficult to find enough incentive for clients to allocate their energy expenditure toward a problem that a different entity can already solve for them. This problem is amplified when more clients join the system because an increased amount of energy is required for each client that is contributing to the solution of a given problem. This is because more clients working on a problem increases the number of tasks and processing cycles each client must perform, which ultimately increases the amount of energy required for the local computation and transmission of the data. According to the data Wang and Associates acquired, roughly 0.15 joules of increased power is needed when 6 clients join into a federated learning system, and this energy increase reaches upwards of 1.6 joules when 12 clients are connected. In a scenario where there may be dozens of autonomous vehicles on the road, increasing the energy requirements and the longer processing times for clients to find a noise-free channel in a federated learning system may not be ideal when compared to the SPAS system utilizing an RL agent. A potential solution could employ the payment compensation portion of the SPAS methodology, but due to the problems brought upon by increasing the client count, it may not be effective. Due to the imbalance of incentives and increasing energy costs when dozens of clients join into a federated learning system, the model may lose effectiveness when compared to SPAS. It would become even less effective if the majority of the clients shared similar preferred channels because it would require more iterations of model cycling. More processing cycles would require more energy and bandwidth, further reducing the effectiveness of the system. Employing the SPAS methodology with a cognitive agent should require less overall energy requirements and processing cycles for both the client and base station at the cost of being allocated a potentially weaker channel. A potential solution to improving the weaker channel allocation issue when adopting SPAS with the RL methodology may be found in employing a real-time or online strategy paired alongside an offline RL strategy. This method is based on game theory, which establishes that an individual sensor would attempt to mathematically predict the actions other helper sensors would take in an effort to formulate its own strategy and secure the best outcome. The online strategy is based on a non-cooperative game in which the helper sensor would first request random access to the base station to require a feedback acknowledgement message. The sensor would then selfishly select a random channel on the network which has the most gain. The offline strategy focuses on using RL to evaluate a sensor's current behavior and improve it greedily so that the random selection will gradually converge into the most optimal one. This hybrid methodology would make it so that MNOs would only have to perform spectrum sensing intermittently while removing the need to negotiate channel allocation with helper sensors. Helper sensors would better have a sense of which channels may be best to select for an upcoming MNO based on the model they have trained when traveling alongside other helper sensors. Compared to the traditional system, this game theory method improves global throughput, which is the sum of individual throughput achieved by each sensor, by roughly 15 megabits when 10 nodes are connected and up to 10 megabits when up to 100 nodes are connected. Overall, this solution requires more energy consumption from the base stations than SPAS with RL, but does not fall victim to the increasing energy cost per client that is associated with federated learning. Ultimately, since it is difficult to discern which system may be best applied over another when being compared as a solution to the improvement of autonomous vehicle cyber-physical networks. Additional research that may improve some of the findings of our research are included in the following links. The first link is about a custom method of improving autonomous vehicle communications called MC-Safe that could improve packet delivery ratio and deadline miss ratio. This method is applied in a pre-crash scenario and proposes a way for vehicles to instantly adapt to their environment so that these vehicles have packet priority. The second link reviews an article which goes over the DeepQ algorithm, which could be used as an alternative reinforcement learning algorithm for a cognitive agent. The third link describes advantages of cognitive radio wireless sensor networks and the potential areas of application they may have. It talks about the ways that we could use wireless sensor networks to improve access to a channel when a given event may occur. The fourth link helps to compare cognitive wireless sensor networks versus traditional radio networks. It also dictates what other performance problems could be solved by applying a cognitive agent to a wireless sensor network.
For lessons learned, our team learned how to use event simulators, AI frameworks, and improved our overall general Linux capabilities. We experienced the level of depth it takes to conduct research on a difficult and upcoming technology. We also learned how to quickly adapt and overcome changes in project scope. Some of the challenges our teams faced this semester include several changes to our project scope. We had minimal experience in AI and event simulators in general. Our team had a lack of coding capabilities, mostly in editing and creating NS3 examples to gather data. COVID-19 forced an online workflow, which led to the inconsistencies in our meetings and did not allow us to meet in person at all. When using NS3, sometimes we had difficulty determining which version of Python some of our NS3 scripts were referencing. So sometimes it would reference Python 2.7 or Python 3.5, and we had to make sure to use the correct commands to call those. And then also for making changes, we had to make sure that there was no discrepancies in that. And finally, we had challenges with getting all the dependencies installed and working properly together. So when installing NS3 originally, there were numerous dependencies that we had to install separately to make NS3 work and open NS3 gem work as well. And there were many times that there were errors and other issues that arose when we were installing these.
So our project boils down to one final question. Is artificial agent-based spectrum sensing as a service viable? Our answer is that yes, it is, and our data supports this answer. Our results show that our agent can handle channel searching and learn through multiple iterations to accurately predict channel activity in order to avoid data collision. Unfortunately, our results from the comparison between federated learning and reinforcement learning are inconclusive. Due to constraints outside of our control, we were unable to perform all the data gathering that we wanted to on this comparison, so we cannot say conclusively at this time which technique is better for this technology. On behalf of our entire Capstone group, we would like to thank you very much for watching, and if you have any questions, you can visit our website at the link provided in the description below this video or here in the video itself. Thank you very much. Have a nice day.